All right, welcome back to another lecture. Today we're going to talk about measures of dispersion. The three measures of dispersion we're going to discuss are the standard deviation, the interquartile range, or IQR for short, and the index of qualitative variation, or IQV for short. There are other measures of dispersion, but those are the three that we're going to focus on. And the idea here is that we've talked about measures of center, right? We've talked about measures of central tendency, which are trying to give us a picture of sort of the average Joe in the data set. But that doesn't tell the whole story, right? Because we also need to know how much variety there is in our data set. And we'll talk about that in a little bit more detail in a second. For now, let's make sure that we're set up with all the stuff we need. First of all, go ahead and download the notes or print them and download the data set that we're going to be using for the examples in this set of notes. But also to compute the IQV that we talked about a second ago, we're going to use this tool right here, this index of qualitative variation tool. And you actually you need to download this. So go ahead and download it. I'm going to show you how to use this tool, and it might be a little bit tricky at first to get it set up, but I'll walk you through the whole thing. So make sure that that's downloaded and set up and ready to go. And it'll have some things up here that we'll need to do to unblock the macro and stuff to be able to use the tool. But don't worry about that just yet. I'll show you when we get there. We should also probably have Art of Stat open in case we need it. Okay, web apps. And we may be using the Explore quantitative data, maybe the Explore categorical data tools. And then also a calculator. So if you don't have a handheld calculator, my recommendation as always is to use the Desmo Scientific Calculator. I think that's a really good one. With all of that out of the way, let's get back to the notes then. Okay, so to get to sort of wrap our brains around why we care about how much variety there is in a data set, take a look at these two, right? So we've got on the left, we've got some data that's supposed to represent the number of chocolate chips in Subway cookies. So it looks like there were a sample of, I don't know how many, 30 or 40 cookies or so was taken. And it looks like there were 2 Subway cookies that had 19 chocolate chips in them. And there were 4 Subway cookies that had 20 chocolate chips in them and so forth, right? And then on the right, we have a dot plot representing the number of chocolate chips in a sample of Quiznos cookies. And so again, here there was only one Quiznos cookie with 19 chocolate chips, but there were a whole bunch, 11 cookies it looks like, that had 23 chocolate chips and so forth. Looking at these two data sets, it's very obvious that there's quite a big difference between them, right? I think we would say the Subway data is much more spread out. There's more variety, whereas the Quiznos data is much more bunched up. We could say it's more consistent, okay? But that story is not going to be captured if you're just looking at a measure of central tendency like the mean, okay? Because, for example, here, the mean of both data sets is the same, even though the data sets are clearly quite different. So I think we've already answered the question here in the second bullet point. They have the same shape, right? So, again, they're both roughly bell-shaped, I would say, right? So same shape and same center. Okay, but they're clearly very different data sets. So which one is more consistent and which has more variety? I would say Quiznos is more consistent and Subway has more variety. Okay. So we need a way to be able to describe that variety. We need to be able to describe the spread of our data. One sort of naive attempt would be to use the range. So the range is just subtracting the largest value from the smallest value, okay? The problem with that is the range doesn't really capture the picture very well, because in these two data sets, they would have the same range, right? Because the largest value minus the smallest value 30 minus 19 would be 11. So here the range is 11, right? 30 minus 19. And here the range would be exactly the same, right? 30 minus 19. And so just looking at the range, you might conclude that, oh, the data sets are both equally spread out, or they're both equally consistent. And that's just clearly not the case, right? So the range is not a very good way to try to measure the amount of spread in the data set. So we need to develop something a little bit more sophisticated, and the standard deviation is sort of the answer to that problem. So what the standard deviation is trying to do, basically, is to see how far on average each observation is from the mean. That's not exactly what the standard deviation does, but roughly speaking, that's kind of how you can think about the standard deviation. It's how far on average each observation is from the mean. These are the formulas that we will use for the standard deviation. So we've got a population standard deviation here and a sample standard deviation here. So when we're computing like a population mean versus a sample mean, there's no difference in the way that we perform that computation. But the same is not true for the standard deviation. There's a key difference here. With the population standard deviation, we divide by n, okay? With the sample standard deviation, we divide by n minus 1, okay? And we'll talk about where these formulas come from and why we divide by n minus 1 with the sample standard deviation instead of just n, like we do for the population standard deviation. But that's a key thing to keep in mind as you're looking at these formulas. Now, otherwise, the formulas are basically the same, right? What we're going to do is take each observation, subtract the mean, and then square that difference. Then we're going to add up those values and divide by either the number of values or the number of values minus 1, right? So it's the same formula. You take an observation, subtract the mean, square that difference, and then add that up for each of the observations, right? So the only difference is that with the population standard deviation, we divide by n, whereas for the sample standard deviation, we divide by n minus 1. Okay. Another thing to mention, just terminology-wise, is the value that we get before we take the square root, right? So when we compute these standard deviations, we're going to do all of these calculations, but then we're going to take the square root, okay? So the number that you get before you take the square root is called the variance, okay? The symbols here hopefully make some sense, right? Because if sigma is the square root of some stuff, right? This, by the way, is the Greek letter sigma. So if sigma is the square root of some stuff, then sigma squared should just be the stuff without taking the square root. And similarly for s, right? If s is the square root of some stuff, then the variance s squared would just be the stuff without the square root, okay? Okay. In Art of Stat, the standard deviation is labeled STD and then DEV, right? So when you put a data, like a list of data into Art of Stat, it'll automatically compute that standard deviation for you. But you may wonder, well, which version is it giving me? Is it giving me the population standard deviation or the sample standard deviation? And the answer is that it's giving you the sample standard deviation. Okay, so to get the population standard deviation, we'd have to use a calculator to make an adjustment. And what we would do is take that standard deviation that Art of Stat gives us, and then we would have to multiply by the square root of n minus 1 divided by n. And we could just do that in the Desmos calculator, right? Alternatively, if you are interested in learning a little bit about how to use Excel functions, then you could use the following Excel functions, right? You could use equals stdev.p for the population standard deviation, or stdev.s for the sample standard deviation. And you could just do that in Excel. So I'll show you how to do it both ways, okay? Let's look at some examples. So number 1 here says compute the variance and the standard deviation of the following sample data by hand, and then use technology to verify your answer. We don't have very much space to work this out, and computing standard deviations by hand is kind of a pain, but that's okay. We'll try to squeeze it in here. Luckily for us, the data set's pretty small, so this shouldn't be too terrible. So if we want to compute the standard deviation, so we're told that this is sample data. So we're going to want to compute the sample variance and the sample standard deviation. So let me just rewrite those formulas so that we have them here. So I think in order to use this formula, the first thing we're going to need to do is figure out, First thing we're going to need to do is figure out what x squared is, right? We're going to need to figure that piece out. And then I think we can do the rest pretty easily. So let's get to it. So the sample mean x bar is just going to be the sum of these observations divided by the number of observations, right? So it's going to be 85 plus 80 plus 93 plus 77 plus 65 divided by the number of observations, 1, 2, 3, 4, 5. So divided by 5, right? There's the sample mean. Let's go punch that into our calculator. Okay, so that's 80. Okay, so then the next thing is to go ahead and compute the variance now, right? So we can say s squared is going to be the sum of each observation minus its mean, which is 80, right? So we're going to do 85 minus 80 and then square that, right? 85 minus 80 squared. Then we have to do the same thing with the next value in the data set, right? Which is 80. So we'll do 80, so we'll say plus 80 minus 80 squared. And then we need to do that with the next value, okay? And then we're going to divide by the number of values in our data set minus 1. At this point, you could punch this into the calculator, into the Desmos calculator to see what you get, or you could do a couple, intermediate steps to get there. But I'm just going to punch it in to the calculator exactly the way it looks and see what we get. So let's head back over to Desmos. And we'll try to punch this in. So again, make sure to just type it in exactly the way that we wrote it down a second ago. Close parentheses, squared. Okay, and then plus 80. I don't even need to write down this term technically because it's just going to be 0, right? But that's okay. I'll put it in there. And then once we've got all that sum in, then we'll arrow down to the denominator and type in 5 minus 1. And it looks like that comes out to 107. Okay. This comes out to 107. Okay, so that's s squared, right? That's the variance. We were asked to compute not only the variance, but also the standard deviation. So to get the standard deviation, what we need to do is take the square root of that number now, right? So if s squared is 107, then s is the square root of 107. Okay, and let's see what that comes out to. That comes out to about 10.3, okay? And this is the standard deviation. So that's how we would do this by hand. Fortunately, I'm not going to ask you to do it by hand. You can if you want. I think there might be a couple homework problems that encourage you to do that. But like on a test or something, I don't think I'm going to ask for you to do this by hand. So let's do the second part of this task now, which says use technology to verify your answer. So let's learn how to do this in technology. And actually, I think you already kind of know how to do it, but let's take a look. So first of all, let me open up that data set, and we're looking at example 1 here. So it's just these values. I'm going to go ahead and copy and then paste those into the Explore Quantitative Data app from Art of Stat. And then it should go ahead and compute that standard deviation for us. And sure enough, it's getting the same answer that we got, right? About 10.3. It does not give us the variance, but that's okay. If you needed the variance, all you would have to do is take this number, 10.34, and then square it, right? So we can paste that and square it. And now, sure enough, right, you've got the variance. It's not exactly the same because, you know, the standard deviation was rounded in Art of Stat, but that's okay. It's close enough. So that's how we would do this in Art of Stat, pretty straightforward. In Excel, if you wanted to do this using an Excel function, if you wanted the variance, then what you would do is just click on an empty cell somewhere in the spreadsheet. And then, actually, let me zoom in on this so you can see a little better what I'm doing. But yeah, just click on any empty cell here in the spreadsheet and then type equals and then type var. And if I want a sample variance, then I'm going to say .s for sample. Okay, and then open up a set of parentheses, and now you can just select the data and then hit enter, right? If you want the standard deviation, then you say equals std ev.s, okay, and open up a set of parentheses, select the data, and hit enter, right? And there you go. So you're welcome to use Art of Stat to do this, or you're welcome to use Excel, whichever you prefer. Excel is kind of nice because it does give you the exact value for both the variance and the standard deviation, but you have to learn how to use the formulas in order to do that, right? So that's the only, I guess, you know, issue with that. Let's move on to the next one. So number 2 here says, use technology to compute the variance and standard deviation of this other data set. And in part A, we're asked to do this if this is sample data. And in part B, we're asked to do this if this is population data. And that's going to make a big difference because of what you have to divide by, right? If it's a sample standard deviation, you divide by n-1. If it's a population standard deviation, you divide by n. So I'm not going to take you through the calculations by hand, but we'll just talk about how to do this in with technology. So heading back over to Excel, let's go over to example 2. And we'll grab our data set here. And let's go ahead and paste that into Art of Stat. And just like that, right, it'll recalculate the standard deviation for us. Now, remember, this is the sample standard deviation. So this will be a good answer for part A. But for part B, we're going to have to fix this up a little bit. Okay, but let's write this down. So our standard deviation for part A from Art of Stat, right, we got a sample standard deviation of 3.46. Right, that's the standard deviation. We were also asked for the variance. So I guess what we would need to do now is calculate 3.46 squared in order to get the variance, right? Okay, and there we go. That's about 12. Okay, so about 12. So S squared is going to be 3.46 squared. Anytime you do a calculation, it's good practice to write down what calculation you performed so that if you get the wrong answer, I can still see like, oh, well, at least I did the work correctly, and I can give you 4 out of 5 points or something, rather than 0 out of 5 points, which is what you would get if all you did was write down the wrong answer, right? Anyway, so this is approximately 12. Okay, this is how you would do it if you were using Art of Stat. If I wanted to use Excel for this, so we would say equals, for the standard deviation, we want a sample standard deviation, okay? And so you can actually just like use your arrows on your keyboard to go down and like select the one that you want, and then hit tab, and that'll select that formula. So stdev.s, and then highlight the data, and then hit enter. There you go. There's the standard sample standard deviation. The variance would be equals var.s. Select the data, hit enter, and there you go, 12, right? So 3.46 and 12. That's how we would do it in Excel. So, you know, if you're showing your work for that, you could say something like, well, I used the stdev.s function in Excel, and then I put in the data, right? And it spit out 3.46. And the variance, I used var.s and then selected the data, and I got exactly 12. Just to be clear, you don't have to do it both ways. I'm just trying to give you options for, you know, whichever way seems easier to you. Now for part B, we want to do the same thing, compute the variance and the standard deviation, but this time we want to do this for population, if we consider this data to be population data. So in Art of Stat, this is going to be a little bit tricky, because Art of Stat doesn't give us the population standard deviation or the population variance. So for Art of Stat, what we would have to do is take the standard deviation that it gave us, 3.46, and then we would have to multiply that by the square root of n minus 1 over n. N in this case is 1, 2, 3, 4, 5, 6, 7, 8. So it would be times the square root of n minus 1, that's 7, over n, which is 8, right? So 3.46 times the square root of 7 over 8. And again, just do your best to try to type it in exactly the way that it looks on the page. Okay, so that's about 3.24. Oh, and I didn't give it the proper label. This is the standard deviation. This is the population standard deviation, sigma. So we should say sigma equals, you know, this number. Okay, and then the variance, sigma squared, would be that number, 3.24 squared, which we can type into our calculator. 3.24 squared is about 10.5-ish. In Excel, this is a little easier, in my opinion, because we're just going to use the same formulas that we used before, only instead of a .s, we'll use a .p for population, right? So the population standard deviation is going to, we'll use the stdev function, and then .p for population. And for the variance, we'll use var.p. So heading over to Excel, let's take a look at what that gives us. So we would say equals stdev dot p, select the data and hit enter, and then equals var.p, select the data and hit enter, and there you go, right? Same values that we got before, but again, in my opinion, a little bit easier to use Excel. But that's just me, you know. You do whatever seems easier to you. So we got, you know, 3.24 approximately, and 10.5. Okay, it's easy to get lost in the weeds, right? To sort of lose the forest for the trees when we start to talk about standard deviations, because performing the calculations is a little bit tedious. So I want to bring it back a little bit and just remind you that the standard deviation is a measurement of how spread out the data are. That is the job of the standard deviation. Its job is to tell us how spread out the data are. It tells us how far on average the observations are from the mean. Okay, a large standard deviation indicates that the data are spread out, kind of like the subway data. A small standard deviation indicates that the data are bunched up, kind of like the Quiznos data. And in fact, I think I failed to mention this, but if we scroll back up, the standard deviation for the subway data is 2.6, whereas the standard deviation for the Quiznos data is 1.4. And if you look at those original graphs, those original box plots, we said this one has a standard deviation of 2.6, and this one has a standard deviation of 1.4. And that makes perfect sense when you look at them, right? The data set with the larger standard deviation has more variety, more spread in the data set. The data set with the smaller standard deviation is more bunched up, right? There's less variety. So the larger the standard deviation, the more variation there is, the more variety there is, the more spread there is, the more dispersion there is, right? The smaller the standard deviation, the less variety, the less spread. Or you could say the other way around. You could say it's more consistent, right? If it has a smaller standard deviation, then it's more consistent, more uniform. Okay. So lots of different ways to kind of communicate the same thing, but that's what the standard deviation's job is. So let's just look at an example, kind of like a hypothetical situation. It says, suppose that you're a talent scout looking to recruit a soccer player for your team. Player A scores 1 goal per game on average, with a standard deviation of 0.5 goals per game. Player B scores 1 goal per game on average, with a standard deviation of 1 goal per game. Part A says, which player has the better scoring average? I'll let you pause the video and give an answer with the with the hint that this is sort of a trick question. Here's my answer. They have the same scoring average, right? Player A scores one goal per game on average, and player B scores 1 goal per game on average. So they have the same scoring average. Part B says, which player is a more consistent goal scorer? Again, I'll let you pause the video and give an answer to that. My answer would be, well, the player that is a more consistent goal scorer is going to have a smaller standard deviation, right? And that would be player A. Player A has a standard deviation of just 0.5, whereas player B has a standard deviation of 1. So player A is more consistent because, well, it doesn't actually say what gender these are. These could be male or female, I guess. So we'll just say they, right? Because they have a smaller standard deviation. Okay, and then part C, whom would you rather recruit and why? Well, that's kind of a subjective question. I don't think there's a right or wrong answer to that question. So I'll let you think through a response and then write something down. Here's what I would say. I would say, on the one hand, you might want to go with player A because they're a little more consistent, a little more dependable. They're going to score 1 goal per game on average, and you can pretty much count on them to do that. Whereas player B is a little bit more of a wild card, right? Player B scores 1 goal per game on average, but they're less consistent about it, and so they might go several games in a row without scoring any goals at all, and then suddenly have a really good game where they score 4 goals or something like that to make up for it. And so who you recruit, it just depends, I guess, on what kind of player your team needs. If they need somebody who's like dependable and consistent, then player A. If they already have like a pretty good team and they have dependable, consistent players, but they just need somebody who maybe can score some goals quickly, then player B might be the one to go for. I'm thinking of a scenario where maybe you put in player B when your team is down by a lot and you're just hoping for a miracle, right? So player B is somewhat of a wild card. You can put player B in there and maybe, he or she will score a bunch of goals. So anyway, I'm just going to leave my answer blank there, but yeah, feel free to write in your response. Hopefully that gives you some idea of how the standard deviation works and what it's used for. Let's talk about the interquartile range. So the formula that we use for computing the standard deviation involves the mean, right? We take each observation and subtract the mean from that observation. But we've talked in the past about how the mean is not a good measure of center for skewed data, which sort of raises the question, if we can't use the mean for skewed data, or if we shouldn't use the mean for skewed data, then we probably shouldn't use the standard deviation for skewed data either. So then what measure of spread should we use for skewed data? And the answer is, there are maybe multiple different ones that we could use, but the standard one is to use the IQR, the interquartile range. And this is actually something that we've seen before when we talked about quartiles back in, I think it was section 1.4. But the interquartile range is just the distance between Q1 and Q3, right? So the IQR is Q3 minus Q1. And it has a similar interpretation as the standard deviation, right? It measures dispersion. It measures how spread out the data set is, how much variation there is. And just like with the standard deviation, the larger the IQR, the more spread out the data. Okay? Which also would mean that it has more variety, or another way to say that is has less consistency. So for example, suppose a data set has the following quartiles, Q1, Q2, Q3. We're asked to compute the IQR. Well, Q2 has nothing to do with the IQR, as it turns out, right? The IQR is just Q3 minus Q1, which in this case is going to be 53.5 minus 48.5. And you can punch that into your calculator, but I'm pretty sure that comes out to 5, right? So the IQR would be 5 here. So that's how we would do it if we were given the quartiles. If you were just given some raw data, like on number 5, then you could use technology to calculate the IQR. And probably using art of stat is going to be the easiest way to do this. So it says below are the weights in pounds of a random sample of soccer players and another random sample of baseball players. Part A says, just based on your common sense, which group do you think would have more consistent weights, and which group do you think would have more weight variety? So I'll let you pause the video and think about that. What I would say is, so we're asked to just use our common sense here, right? So I'm trying to ignore the numbers for now and just say, well, okay, what do I know about soccer versus baseball? Soccer players tend to be running around the field the whole time. Baseball players, not as much. It's not that baseball players are totally inactive, but they're not running around the field constantly the way that soccer players are. So I would guess that soccer players are pretty consistently fit, whereas I've seen some baseball players who are not quite as fit, let's say. So I would guess that baseball players probably have more variety in their weights. I think soccer players are probably of a more consistent weight than baseball players are. Maybe an even better example would be like soccer players versus football players, right? Because with football players, yeah, you're going to have a lot of different shapes and sizes, right? But anyway, I would say soccer players have a more consistent weight. Baseball players have more weight variety. Part B says create a frequency histogram for each group and identify their shapes. Why would it be better to compare medians and IQRs than means and standard deviations in this case? Well, I would guess that it's probably because at least one of the data sets is skewed. But the only way to know that is to actually create the frequency histograms. So let's go ahead and do that. We're going to need to do that anyway in order to get the IQRs. So I'm going to, let's actually open up art of stat first. So I'm going to need to open up a new Explore Quantitative Data. And what I actually want to do is compare a couple of groups. So I'm going to go up to the tab on the top and select several groups so that I have a place to put in different things. I'm going to put in my own data. And yeah, I just have two groups, baseball and soccer. Okay, and now let me get my data. So for soccer players, and for baseball players. We were asked for frequency histograms, so I suppose we should take a look at some histograms here. They actually don't look too badly skewed to me, looking at them here. They both look fairly symmetric, so I would say actually probably you could use the mean and the standard deviation rather than medians and IQRs here, but that's okay. We'll go ahead and compare the IQRs anyway. Since that's what we're going to be asked to do in part B. So why would it be better to compute? Well, I promise that on a test or a problem set, I won't do this to you. It's never my intention to intentionally trick you, right? So if on a test I said, why would it be better to compare medians and IQRs? Then the answer would be because the data sets are skewed. It's just in this particular example, for whatever reason, I didn't come up with a very good example for this. Anyway, but no, these data sets aren't very skewed. And so I would say, actually, you probably could use the mean and the standard deviation. But anyway, the moral of the story is this. For skewed data, that's when we use the median and the IQR. So then part C says, based on IQR, which group has more weight variety? And based on the IQR, group 1 has an IQR of 25, where group 2 has an IQR of 30. So group 2 has more weight variety. And I think group 2 was baseball, right? So based on IQR, we would say, well, for the soccer players, right, the IQR was 25. And for baseball players, the IQR was 30. So baseball players have more weight variety. Okay, so that's the IQR. Let's take a look at the IQV. So this is the last measure of dispersion that we'll discuss in this section. And you might guess what we use the IQV for. For quantitative symmetric data, the measure of dispersion we use is the standard deviation. Okay, so standard deviation for symmetric quantitative data. For quantitative skewed data, we're going to use the IQR, like we just talked about. But then this raises the question, well, what do we do for categorical data? What measure of dispersion can we use for categorical data? And that's where the IQV comes into play. So the index of qualitative variation, or IQV, is a measure of spread for categorical data. This is the formula for the IQV. And we're not going to practice using that formula by hand, but just to kind of explain what it means, K is the number of different categories in your data set. And these p hats are the sample proportions of each of those categories. So you take the sample proportions, square them, add them up, right? And then do 1 minus that answer, multiply that by k, and then divide by k minus 1. So it's a little involved, which is why I'm not going to have you do any of this by hand. But here's what I would like you to know. The IQV ranges from 0 to 1. So the smallest the IQV can ever be is 0, and the largest it can ever be is 1. Just like the standard deviation and the IQR, the larger the IQV, the more variation. So an IQV of 0 would indicate that there's no variation in the data set. All of the category, or all of the data is in one category. And an IQV of 1 would indicate the maximum amount of variation, right? The data are all equally distributed across all the categories. And here I think is a good kind of picture to show what the IQV does, right? So this first histogram here, or not histogram but bar chart, these are all supposed to represent the sales on the 5 weekdays, Monday through Friday. If you have the same volume of sales on every single day, Monday, Tuesday, Wednesday, Thursday, Friday, then that means your sales are equally distributed across the days of the week. And so that would be the maximal amount of variety possible. So you have an IQV of 1. On the other hand, if you had a situation like this where there were no sales on Monday, Tuesday, Thursday, or Friday, and instead all of the sales took place on Wednesday only, then that means there's absolutely no variety, right? Your data set would just look like Wednesday, 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 right? There's no variety there at all. And so your IQV would be 0. Okay, but anything in between could happen, right? So you could have a situation like this where, yeah, there are some sales taking place on every day of the week, but more sales on Wednesday than on Monday or Friday. And so there's a little less variety here than there was over here, okay? Here, there's less variety still because you at least have sales going on Tuesday and Thursday, but there are no sales going on Monday and Friday, right? And so forth, right? So this is how we interpret the IQV. For example, let's say you ask a random sample of 65 people from each state which snack they prefer at a Super Bowl party: corn dogs, nachos, popcorn, buffalo wings, or pizza. Which state likes a greater variety of snacks at their Super Bowl party? Minnesota with an IQV of 0.7 or Wisconsin with an IQV of 0.65? I'll let you pause the video and write down your answer. But here's my answer. Clearly, Minnesota likes a greater variety of snacks because they have a larger IQV, right? So Minnesota. Minnesota. Because they have a larger IQV. Okay. Art of Stat does not compute the IQV, so we'll have to do that in Excel. And that's where that workbook comes into play that I had you download at the beginning of the lecture, right? The one called Index of Qualitative Variation, IQV. So I'm going to show you how to use that tool now as we work out example 7. Actually, maybe before we take a look at example 7, let's just make sure that we've got the tool all set up and ready to go. So when you download this from Canvas, you'll open it up and it'll look something like this. So the first thing you'll need to do is click on the Enable Editing button in the yellow ribbon across the top of the screen. But then after that, give it a second. Okay, but then after that, you might get this little message that says, oh, there's a security risk here. Microsoft has blocked macros from running because the source of the file is untrusted. Now, you can click on Learn More. You can Google like how to unblock Excel macros, right, to figure out how to do this. Here are my suggestions. Okay, if you're using a PC, then the first thing that you're going to want to do is close the file, and then you're going to find the folder where you saved the file, go to Properties, and then in the little dialog box that opens up, you'll uncheck the unblock box at the bottom. So let me walk you through that, okay, since I'm using a PC. I'm going to close this down. Now, I saved that in my Downloads folder because I downloaded it earlier. So I can just click on Downloads and click on this little File button. And I'm just trying to get to the place where my file is stored so that I can right-click on this. And then I can go to Properties. And then in this little dialog box, I'm going to want to check Unblock, okay? because I want to unblock the properties of that file. So I'll say OK. So now if I reopen this, so double click on it to reopen it, I'll have this yellow ribbon here that says enable content. And now I should be able to use the macro on this. The macro is the tool that we're going to use to actually compute the IQV. So that's what you would do if you're using a PC. Now, if you're using a Mac, then I can't really help you in this video because I'm not using a Mac. But if you follow these instructions, it should be pretty straightforward to unblock the macro so that you can use it, or to enable the macro. And if all else fails, again, right, you can also just Google this, right? How to unblock Excel macros or something like that. And then you can follow the suggestions they give you there. Now, with that all set up, let's head back over to the example, right? So number 7 here says, a student walked around her neighborhood and recorded the number and type of each tree she saw. Her observations are recorded below. Create a relative frequency bar chart and use it to identify the mode and the modal proportion, and then compute the IQV. Okay, so we've got a few different tasks that we're asked to perform here. I'm going to head back over to the computer so that I can do this. First thing I'm going to want to do is grab my data. So this is for example 7. I'm going to do Control-Shift down and then copy C to copy. And to get the frequency bar charts, I'm going to go ahead and open up and explore categorical data app. And I have my own data, and I'm just going to go ahead and paste that there. So there's my frequency bar chart. If I want, so from the frequency bar chart, we were asked to identify the mode. The mode is clearly Cypress, right? That's the category that occurs the most frequently. We were also asked for the modal proportion. Well, if you hover your cursor over this bar like I am, it shows you the percent right there. It says 23.81%. You could also see that here. Cypress has the greatest frequency. So Cypress is the mode. And the relative frequency, or in other words, the proportion, is 0.2381, right? So 23.81%. Okay, so that's the first part of the question. Let's write that down. So the mode equals Cypress, and the modal proportion P hat is 10 out of 42, which is about 0.238. Okay, as for the IQV, you'll notice that Art of Stat doesn't compute the IQV for us, unfortunately. And there's no way to get it to do the IQV over here either. So what we're going to do is we're going to, once again, copy our data. I'm just going to recopy it. Control-C. And then I'm going to open up this index of qualitative variation tool, and I'm going to paste the data. Now it says, once you've unblocked and enabled the macros on this workbook, you're ready to use the tool. First, paste your data into the spreadsheet. If it's raw data, which is what we have, paste it into column A. Make sure that the first cell, A1, is the name of the variable, and that the data begins in the next cell, A2. Okay, so I don't want to paste the data right here. I want the name of the variable to be here. So actually, let me go back and recopy this so that I can get the name of the variable, which is tree variety. So Control-Shift down, Control-C, and then I can paste this here, Control-V. Okay, once you have the data in the spreadsheet, click on View, and then Macros, and then select View Macros. So I'm going to go to View, Macros, and View Macros. This might look a little bit different for you, depending on the machine that you're using. If you have raw data, it says calculate IQV from the menu. So calculate IQV is the one I want, and then run. And just like that, it computes it for us and gives us the answer right here. The IQV is 0.956-ish. So let's say 0.956. Okay. So that's how we would compute an IQV from raw data using that tool. Number 8. So a last example here, and I know that this has been a long one, so thank you for hanging in there. Number 8 says, the racial compositions of 3 states in the United States are given below. We've got the various races listed, and then we have, it looks like we want to compare New York, California, and Wisconsin. We're asked to create a side-by-side relative frequency bar chart for the racial composition in these states, and then compute the IQV for each state, and rank the states from least to most racially diverse. Okay, so once again, let's go play around with that a little bit. I should have that data here. Yes. Okay. So let's go to Art of Stat. I only have... Oh, no. I can do... Oh, I don't have individual observations. What do I have? A contingency table. Okay. So I can go ahead and put in as many rows and columns as I want. In this case, I need 1, 2, 3, 4, 5, 6 rows. And 3 columns, right? So that I've got a column for New York, a column for California, and a column for Wisconsin. Okay, and then the races, I can put those in as well. Other. Okay, I'm going to go ahead and I'm just going to put in these as decimal numbers, relative frequencies. So for New York, it's 9.3%, and then 17.6%, and so forth. Okay, this is what you should end up with. If you've put everything in correctly, all the columns should be 1, right? All the column totals should be 1. Anyway, so here are the racial compositions. I wonder if, yeah, this is a little better. If we do the conditional distribution by columns, then we can see the distributions by each state, and that's a little bit nicer, right? So instead of by rows, click on by columns. And that gives us a kind of a nicer picture, in my opinion, because we can see now that Wisconsin has a very high bar for the racial category white, and New York also has a fairly high bar for the racial category white. California also has a fairly high bar for that, but it has an even higher bar for the racial category Latino. So just looking at these distributions, I would say it looks like California probably has the most diversity of these 3 states. I would say California. But the only way to be absolutely certain of that is to actually compute the IQVs of these 3 states to see how they compare. So let's do that. So I'm going to open up this IQV tool again. It says if it's a table, which is what we have, what we need to do is paste the table into the spreadsheet with the categories in column A and the counts or proportions in column B, and do not include the totals. And I'm not sure that it can do this for all of the data sets at once, so we'll just have to do them one at a time. So first of all, I'm going to delete that. I did that by just selecting the data and then hitting delete on my keyboard, not backspace, but delete. And that'll get rid of all those. And that gives me room to put in some new stuff. So let me do this. So I'm gonna I'm just going to do New York. I'll do these one at a time. So I'm going to do New York, copy, and paste. And then I'm going to run the macro. So view macros. This time I want to calculate an IQV. I don't have a frequency table. I have a relative frequency table, right? These are relative frequencies. And there we go. Okay. So I'll write that down for New York, 0.793. Okay. And then we'll go back and do the same thing for the other two states. So let me get rid of this. And I'm going to put in California. And then rerun the macro. So macro, view macros, calculate from relative frequencies. So that's an IQV of 0.832-ish. Okay. And then last but not least, let me get rid of this. So I'll select it, hit delete, go back over and grab Wisconsin. Oops. And paste Wisconsin in here. And view macros, calculate from relative frequencies. 0.680 approximately. Okay, 0.680. I guess I should be using approximate signs on all of these, right? Since I've been rounding. Okay, so I think that this goes along with exactly what we saw in the bar charts, right? It looks like California is the most diverse, Wisconsin is the least diverse, and New York is somewhere in the middle. So it says rank the states from least to most racially diverse. So least diverse is Wisconsin. Most diverse is California. And then somewhere in the middle, right, we've got New York, right? So there's our ranking from least to most diverse, which again, I think corresponds nicely with what we see here, right? California is pretty diverse, right? There's a lot of spread, a lot of variation here. New York is also fairly diverse. Wisconsin is the least diverse of the three. Okay, so just to kind of summarize what we've talked about, and I know that this has been a long section, but what we talked about today are measures of dispersion, okay? Standard deviation, interquartile range, and index of qualitative variation. We use those three measures of dispersion for different kinds of data, right? We're going to use a standard deviation if we have numerical symmetric data. We're going to use an interquartile range if we have numerical skewed data. And we'll use the IQV if we have categorical data. This corresponds with the measures of center that we talked about in section 1.6, right? So you should always use the mean and the standard deviation together. You should always use the median and the IQR together. And you should always use the mode and the IQV together. So I think this chart is kind of helpful to help you know what kind of measure of center and what kind of measure of dispersion to use based on the type of data that you're looking at. Now, the rest of this information is just bonus information. And so what I'm going to do is stop this lecture and I'll record this information in a separate video. And you're not required to watch it, but you can watch it if you're interested. So the bonus topics that I want to cover are, first of all, a little bit of information about relative measures of dispersion. And then second of all, I want to go through how we come up with the formula for the standard deviation. So if you were curious at the beginning of the lecture as to, well, but why is this the standard deviation? We'll talk about that in another video. Thank you for hanging in there, and I'll check in with you in the next lecture.